Okay, so welcome back. This is going to be a review and teardown and even an LTSpice simulation for those who are engineer types. We're going to actually reverse engineer what the circuitry inside of this and see how it works. And there's some surprising design concepts used in here in order to make this a very cheap, inexpensive device that are kind of interesting, and honestly, I didn't know about them until I looked into this. So we're going to reverse engineer the circuitry here and simulate it, and just give an overall review for folks who want to know what this is and what the limitations are. And there are a few limitations that you need to be aware of, I think. So first of all, if you look at the box here, it's 720 lumens. Now, 720 lumens, if you're not aware, is about the same as a 60-watt light bulb. So imagine, if you're going to ask how bright is it? Well, imagine a white 60-watt light bulb that's directional. Again, this is a directional light. These LEDs are directional. It's not going to light up your room. It's going to be a directional light, about the same as a 60-watt light bulb. So that's kind of the answer to how bright it is. Depending on your usage, it may not be enough, or maybe enough. 60 LED lights. These are all LEDs in a big array. The good thing about this is it's not just a 60-watt light bulb. It's a very efficient 60-watt light bulb. So that's one of the pros about this. It doesn't use a lot of power at all, and we'll see why. It's a very efficient light. 2 brightness modes, it says up here. And it's basically a high, low. There's also an SOS mode that I don't think is of much use, and in my case, it didn't even work, so we're not going to talk about that. But basically, it's a high and low mode. With mine, it's about the same, high and low. You can't really distinguish the two, so what do you want for $20? No batteries needed. You see up on the box, no batteries needed. Portable. Perfect for power outages, camping, auto, and home. Again, this is more about being a portable device, and we'll talk about that. And there are some negatives about this you need to be aware of, and we'll talk about. So the price, about $15. I've seen it for as low as $15, can be $25, somewhere in that range. Again, 720 lumens, about the same as a 60-watt light bulb. Now, what's important, and when I've seen a couple other reviews of this, they haven't mentioned this, but to me, it's very important. The instructions, if you look at the instructions, and I know a lot of reviewers bypass instructions because they're not fun, but if you look at the instructions that come with this, the first thing it says is when charging this, you have to first turn off the switch, turn the LEDs off, put the switch in the off position. What they're saying is you cannot have the unit on. You can't have the LEDs on while you're charging it. Now, if you think about that, that is a huge pain. And in my case, it caused a big problem. What they're saying is you need to first charge it, make sure you remember to charge it before you use it, right? What I did is, unfortunately, I left it on, plugged in and charging with the lights on all night, and I think that caused a bit of damage to the battery. So, again, you have to plan. With this thing, it's not you just grab it and go. You have to charge it when you don't need it, all right? Now, the next thing is, first time you use it, you need to charge it for 24 hours or 25 hours, right? All day, you got to charge it first. These are lead acid, old lead acid, in my view, kind of junky batteries. Now, the other big thing about this, the charging time is 8 to 10 hours under normal conditions. Now, think about that. If you're going to charge this to full, you need to charge it for 8 to 10 hours continuously. It's very, very slow charging, which means if you look at the first item, you can't have the lights on. You're going to charge it when you don't need it, which means probably while you're asleep, you got to remember to go over to this thing, plug it in, and start charging it, and then unplug it when you wake up, all right? Now, when it is fully charged, this is what the instructions say. The light bar can be used continuously for about 5 hours in the high mode. So what they're saying is you charge it for 8 to 10 hours, unplug it, then you can use it in the high mode for 5 hours, all right? And about 12 hours in the low mode. So think about that. You're going to have to charge this all night. You can use it during the day, but only for 5 hours if you're going to use the high mode, which I always use. So these are some big limitations, right? This is about charging it at night, using it when you're not asleep, okay? In my view, the summary of this thing is it's a $20 portable. This is all about being portable because, you know, that's what they're focusing on. Charging it, grabbing it, and go. It's a $20 portable 60-watt light bulb that you have to remember to charge every night. So if that's fine with you, that's great. But just remember, these are some big limitations. Okay, so here's the light bar we're going to look at. Again, it's between $15 and $25. It's got 60 LEDs here. You can see here it's plugged into 120 volt AC directly. And the first question is probably, how bright is it? Well, I'm not going to go through and do a bunch of tests on how bright, but I can tell you it's about the same light output as a 60-watt light bulb. So if you're familiar with a 60-watt light bulb, it's about the same. Just keep in mind it's kind of directional, right? I mean, it's only going to shoot in one direction. That's why, in my view, it's pretty much mostly going to be used for, you know, lighting under a countertop or over a countertop or lighting your bench. Again, if you're outdoors, you might use it for other things. Keep in mind that these LEDs are kind of bright, so you don't want to generally look at them. They're kind of annoying, probably not going to hurt you. But that's basically it. It's a big plastic case. You can see it's got some stands here. It's got one where you can hang it from the wall. Again, I'm not sure why you want to, because you don't want to be looking out of the corner of your eye at these LEDs. Maybe you do. The other one I think is even less useful, is a stand where you can pretty much stand it up. And, you know, if you don't mind it staring at you out of the corner of your eye and, you know, annoying you with the bright lights, what I do is I use these mounting brackets. And what you do is you screw some wood screws with their tapered heads into the wood, and you just mount it here. Again, you're going to need wood screws with the tapered heads because they'll fit. The other ones, you know, regular metal screws or something, you might have trouble sliding them in these slots. So that's basically it. On the outside, you can see it's marked Bell plus Howell is the manufacturer. Now, some of the old timers may remember Bell and Howell. They made movie cameras and movie projectors and stuff. So apparently what Bell and Howell did is they sold their consumer division, consumer products, and Bell plus Howell is their consumer division that they're no longer associated with. What used to be their consumer division, apparently it's no longer related to Bell and Howell, but they somehow get away with Bell plus Howell. I don't know how they do that. Here's the switch, on-off switch. You can see it's off now. It goes to high, off, low, and SOS. Now, some of you may remember Morse code. SOS means save our ship, and apparently when you put it in this mode, it's supposed to send out some Morse code light flashes to indicate that you're in trouble. It doesn't seem to work for me, and I don't know why you need it anyway unless you're out in the wilderness and whatever. So again, high, off, and low. And here you've got, again, the 120 volts direct AC, and you've got an LED that is lit when this is charging. Some people complain that their light stays on even when it's not charging. You can see with mine it turns off. Again, not a big deal. But that's basically it. Again, this thing requires 8 to 10 hours of charging. It's really basically just useful, in my view, as a portable 60-watt light bulb that you have to remember to charge every night when you're asleep. So the next thing we're going to do is we're going to take this apart and kind of reverse engineer it for the technical folks here and see what's involved in making this work for such a cheap price. Okay, so what I'm going to do is just take off this top. I've already unscrewed it. And you can see here's the LED array. I'm taking that off, and this is the internals. Now ignore this terminal block. I added that so I could do some measurements, so that doesn't exist. But basically, neither does this white wire, by the way. But basically, it is the two wires, the red and blue wires going out to the LED array. You've got this little tiny board in here and this big capacitor. You've got the AC coming in, these white wires going into this board. You've got the switch, and you've got these wires going to the board. And here you've got two 4-volt batteries, and they are in parallel. So my guess is these are like 2 to 4 amp hour batteries. But again, they're in parallel. So it's 4 volts, and that's about it. So what we're going to do is we're going to look deeper at this circuit and reverse engineer it and see how it works and see what the limitations are. Again, I said you can't have this on, and you can't have the lights on and also be charging the batteries. Now I'm charging, and I can turn this on, and you can see the lights will come on, but it's not charging the battery. It's using all of the input current to charge the LEDs, not the battery. So and we'll also look at some of the downsides to this cheap design and some of the problems you can get into. Okay, so here's a photograph of this tiny board that's running this LED light. And you can see here on the top, I've got the 120 volt AC coming on these two white wires. And this is a full bridge rectifier. So it's taking the 120 volts and it's running over here. We've got these diodes, and down here we've got some resistors under these wires, and we've got these white, red, blue, black wires going to a switch, and then going to the LEDs themselves, we've got this L plus wire going off, and we've got an L minus blue wire, and those two, the red and the blue, go off to the LEDs. So what I did is I kind of reverse engineered this, and I drew out the circuit in LTSpice to do a simulation to see if I could better understand exactly how this works and what's going on. So as you can imagine, it's kind of difficult. These are not marked, the bridge. This is an M7 diode, but the transistor down here and everything are not really marked. So anyway, before we get into the exact details of this, I want to introduce you to a circuit that you may not be familiar with, a type of circuit that apparently, and I wasn't familiar with it either, I had to go searching around, but it's used in very, very, very cheap devices where you need to convert your 120 volt AC very cheaply into a DC value. So what I want to look at here is a portion of this circuit that that's utilized in this device. And if you look at it, you might be able to recognize the circuit in general. Over here on the left, we've got the wall 120 volt AC 60 hertz, 170 volts peak, 120 volts RMS, 60 hertz. And it's feeding into this, looks like an RC filter kind of thing. Some sort of input filter, block DC, whatever. Here you've got a full bridge rectifier, which of course you're probably familiar with. And of course on the output you've got a filter capacitor, 100 microfarad, and then you've got your load here. So pretty simple circuit. And if you think about it, you got, 120 volts AC coming in, 4 volts load. Wait a minute, how can you go from 120 volts AC through a bridge rectifier in this little filter circuit to 4 volts? Well, that's what I'm talking about when I say that they are using a very, very cheap and simple circuit to just barely get by. And what you might not know is the way they do this is it all focuses on this C1 capacitor, okay? Now, I originally thought it was just a simple filter. No. This C1 capacitor is the way they convert from 120 volts to 4 volts. Now you might be scratching your head as I was. To figure out how they do it, first of all, this is 60 hertz. So if you look at the impedance of this capacitor at 60 hertz, it's about 3.8 K ohms, all right? So if you divide 120 over 3.8, you're going to get tens of milliamps, right? So now you're down to tens of milliamps going through this 4 volts rated LED circuit. And this is, again, this is 60 LEDs in an array, and you're feeding that. So if you're going to limit your current down into tens of milliamps, you can see that if you multiply, 10 milliamps times 300 ohms or whatever, you could get 4 volts. So if you make a little graph of what the volts developed across the load versus the load resistance is in this case, if I've got a 4 volt rated load, I need to have a load resistance in this range down in here, maybe 100 ohms or 300 ohms or whatever. But if that ohm value of the load starts getting big, you can see I'm starting to get 10, 20, 30, 40, 60 volts. If I get 10K ohms, I'm going to get these very high voltages across the load, and it's just not rated for that. So as you can see here, I've got a filter capacitor rated 25 volts. If this ohm value gets up to big numbers, you're going to blow up this capacitor. So that's why this is a cheap and nasty way to do it. Now, the worst case is, of course, if this is an open circuit. If that's an open circuit, you're going to see hundreds and hundreds of volts across this capacitor, and you're going to blow it up. This is a dangerous circuit if you're going to get an open circuit here. But that's basically what they do to get your 4 volts. This is called a capacitor dropper circuit, right? You use a capacitor to drop the voltage across the load. Again, a very cheap and nasty way to do it, but it kind of works. Now, if we look at the actual circuitry for our device, our LED device, you look down in here, and this is basically what we showed before. You've got the AC coming in, you've got the capacitor, you've got the bridge, you've got the filter, and then over here, I've got the LED output, all right? So we also have a 4 volt battery here, and we have a transistor down here that has a set of biasing resistors, okay? And they are connected to this switch. Now, again, I said there was a switch that's off, high, low, and SOS. Now, the way I'm showing it here, it's in high mode. And what that has is a direct connection to a 100 ohm resistor, biasing resistor, that is biasing the voltage and presumably turning on this transistor when you're in high mode, which allows current to flow through the LEDs, right? If you're off, this isn't biased and the lights go off, all right? If you're in low mode, it inserts an additional 1K, which changes the current through this resistor and drops down the current through the LED array and drops down the brightness, presumably. Doesn't seem to be that way. It looks like the same either way, but So basically, it's a fairly simple circuit. Now, if you look here, if you are charging, say you're going through this charging circuit and you're getting a voltage out of here, what this is going to do is it's going to provide a voltage to this battery, all right? And since this switch is off, there's going to be no connection, so you can't bias this transistor on. There's not going to be any voltage. This is going to be an open circuit right here on the switch. This won't be biased, the resistor will be off, and therefore there will be no current flowing in the LED. So you can basically take this right-hand section of the diagram and erase it, because now all you're doing is you're connecting the charging to this battery and you're charging the battery. And the path is it comes out here, goes up, positive, down, positive back in, and there's the entire circuit. All right. Now, if this is off, if your charging is off and it's unplugged, and you turn this switch on, now you are biasing this on, and you've got the battery feeding directly through. It's biasing on this transistor, and you're getting the current flow through the LEDs. Now, the other interesting thing about this circuit is I mentioned before that you can't have the LEDs on at the same time you're charging the battery. And the reason for that becomes visible when you look at this circuit. Basically, when you're charging this battery, because of this high impedance, you can only deliver like 200 milliamps of current charging the battery, and it takes a long time to charge because this capacitor pretty much limits you to 200 milliamps. Now, the actual LED requirement is almost twice that. Okay, so if the LED is on, this guy is not going to be able to charge the battery because you're feeding the LED. So again, it's a cheap and nasty solution that, one of the big problems here is you can't charge the battery at the same time you've got the LEDs on. The LEDs are going to be on and the battery's not going to be charging. So it's, again, cheap and nasty. So anyway, I did LTSpice simulation. The numbers looked about the same as measuring it on the scope and the meters. I may do another video showing the results of the simulation versus the actual measurements. But in any case, I hope this helps. Take care and have a really good day. Thanks.